Okay, so let's get to the core of what dynamic programming is. We had two functions. We had the recursive function for fib, and then we have this new iterative function for Fibonacci. Okay? And we could, in fact, we could make it even better with the iterative version. Over here in this Fibonacci, we were storing all the values of all the Fibonacci numbers up to n in an array. We don't really need to do that. For Fibonacci sequence, we only need to store the previous two values in order to compute the next value. So we can make this Fibonacci function even more space efficient by only storing the previous two values. Okay? So, I mean, so the iterative version of the Fibonacci sequence is much, much better than the recursive, right? Much, much computationally better. So, dynamic programming is what is known as smart recursion. In the normal dumb recursion, we were computing the same values over and over and over and over again. But if we are smart about it, we could see that there are only n problems. There are only n possible instances of this of fib. Okay, there are only n values that will go into the input of this function. So instead of calculating n equals to 0 over and over and over again, we store n equals 0, and then we give it back when we need it. And dynamic programming is smart recursion plus explicit memoization. And we say explicit because, again, the function memoization depends on us. We're the ones that are programming in the memorization of the problem instance solutions, not the compiler. There are actually languages, functional languages, that do have what's called implicit memoization, that basically have hash tables that record when a function gets called, what the input is, and keep the value in case that call comes through again. There are those advanced types of programming languages, but they haven't caught on just because developing the compilers for them is super, super, super expensive. So all we need for dynamic programming is, as we saw with the Fibonacci example, to have a table of outputs for each instance and to fill this table in the right order. And doing these three things allows us to remove the recursion. So let's say we have a recursive program. Let's step away from Fibonacci and abstract it even more, and say we have a recursive program foo that takes in some input x. So we have a program foo takes in some input x, and we know that the number of distinct subproblems that foo generates is at most some function times n. Okay? Okay, so we know this recursive function generates at most a to the n function calls, and we know this function spends at most b to the n time computing stuff. Okay, so it spends if the only computation in foo is simple comparisons, is a finite number of comparisons, then this b of n could be O of 1. If the work inside foo of x is, I don't know, sorting values, then the function could be O of n log n. Right? Doesn't matter. It doesn't matter what specifically b of n is. We just know we have some amount of work and we have some number of recursive calls. Okay? So we know that given a input of size n, we generate some number of subproblems, and given a and the function itself takes out most n time, b of n time. Okay, so suppose we memorize the recursion. Okay, we store and retrieve solutions to the pre-computer problems. Remember, we have a to the n problems. Okay, we have a to the n problems, and for each one of these problems, we're gonna declare, I don't know, an array. Okay, we're gonna have a great indexing method. Don't worry about indexing costs or anything like that. We're able to store the input, i.e. the instance, the problem instance, and the output, the whatever the return value is, for each of these a to the n problems. What is the upper bound of the running time of the memorized version of foo if the size of x is equal to n? Any idea? We know that x of size n will generate at most a to the n subproblems, and each of those subproblems takes at most b to the n work. So using this idea of memoization, we only need to calculate a to the n values. And to calculate a to the n values, each value takes b to the n time. So the total amount of work takes O times a to the n times b to the n. Okay? And that's the beauty of memoization. That's the total time it takes for a recursive function can be constrained in potentially a polynomial equation, as long as the number of distinct subproblems is also polynomial. Okay, and we'll see an example of that next. Thanks.